And up next in the queue is Alex, and he's going to talk about Serde. Thank you.
Hi, so I'm Alex, and one of my passion projects I've started this year is a kind of document database. Has anyone heard of CouchDB? Okay, a couple of people. It's a pretty obscure one. It's lacking a bit of love, but it has a lot of nice features, and I wanted to implement something like that, but better. So the main thing that I wanted to do was have a document database that can store JSON documents, but those documents conform to a predefined schema. So when I say schema, so obviously if I'm storing JSON documents, then, see, nerves. So I want to make sure they conform to a schema. How do I represent a schema in Rust? A simple approach is just to use an enum, where you enumerate through the different kinds of values, and then some types like arrays and structs, they're going to embed their own values. Like arrays have element types, and structs have a type for each of their key value pairs. So that creates a tree on the left. So the goals for this part of the project that I want to kind of talk about, how I went about and how I solved it and the insights I had, like I said, was to store these JSON documents on disk, and as they come into the database, I wanted to validate them against this schema. And the great thing about having this type-safe schema beyond just, I guess, having more control over what data is in your database is it actually lets you save a lot of space, and more space than even if you were to use like a generic binary encoding like BSON. So for example, if we've got a schema like on the top right, name, age, hobbies, and a JSON document below that which conforms to it, we don't even need to store those keys, name, age, hobbies, those strings, like you would say in MongoDB. You just store them once in that common schema, and then your 1,000 million documents don't need to, and you save some space there. And so when I was implementing this, I wanted to make it as space efficient as possible, and then optimize the performance as much as possible. So the first approach I took, was kind of like the simplest approach I can think of. I'm going to backtrack a bit, because I wanted to do all this, but I wanted to take advantage of Serde, right? It's the standard that we use in Rust for serializing and deserializing. Serde JSON I would use for serializing and deserializing JSON. So how do I take advantage of that to work with JSON, but then I guess integrate it with my own custom binary encoding and decoding? So the simplest approach is to use this value object that comes with Serde JSON. Again, it's a simple recursive enum that can represent arbitrary JSON. So you can take the JSON text, parse it into this structure in memory, and then run the custom encoding logic to turn that into compressed bytes, and then go back the other way. It's a pretty simple approach, but the biggest downside is it costs performance, because you're doing this intermediary step of constructing the value, and it's wasting memory, and it's particularly bad because it is this recursive thing. You're having all these really small heap allocations, which can really kill performance as well. So I wanted to do better, and so I needed a way of integrating with Serde's ability to serialize and deserialize. And to do that, you basically have to implement the serialize and deserialize traits. And that posed a couple of challenges. So what I realized was that when you use the derive macro to implement serialize and deserialize, it just, whatever the shape of the struct or enum is, that's what's going to be reflected in the JSON. What I realized is when you implement this trait yourself, you don't have to follow that rule. The output JSON can be completely divorced from what the struct is. And so this insight is what allowed me to, do this decoding logic where I've got not just the encoded bytes, but the schema alongside it, which tells you how to interpret those bytes, because it might be a string, it might be an array, it might be a number, so the same bytes are going to have different interpretations. So how do you integrate that with how Serde works? So it's pretty simple. You just put the compressed bytes, you put the type in the single struct, and then on that struct, we implement serialize. And then that will interface with the JSON serializer so that it can do the work of emitting the curly braces and commas and free me from having to write my own stringify logic. And just because obviously trying to compress this all in 10 minutes, I can't go into great depth, but just to give a taste of how that works in practice is you do a match statement over that type enum. So if it's a U64, there's a typo in the slide, it's meant to actually interpret those bytes as a U64 before it passes to the serializer. And then for a compound structure like an array, that's where we get recursive. So we begin serializing a sequence, which for JSON is going to correspond to an array. We read out those elements from the bytes, as such, and then we call serialize element, and then we reconstruct a new instance of that typed bytes struct, and that calls serialize, and that comes back to the serialize. So that's how we get that recursive behavior to implement the whole process. So the deserialization, so the serialization was pretty easy. The deserialization I got really stuck on for a long time. I could not figure out how to do it. You'd think intuitively they would just kind of be symmetric to the serialization process. But what I ran into was the fact that when you serialize something, you have access to this value, this instance of an object that you're serializing. So you can put in any context, any data you need to then get that output JSON. But when you're going the other way, using the normal deserialize trait, you can see it's an associated method that doesn't take self. So you don't get that context that you need to turn that, that JSON input into your compressed bytes. So I couldn't figure out how to get the schema into it, because the schema is going to dictate whether the input's even valid in the first place, and then what the keys are and how I turn that into the compressed bytes. So eventually I found deserialize seed, which seemed to be designed for this exact use case. Instead of implementing it on the output type itself, you implement it on this thing called a seed, which is essentially the context for the deserialization process. And then you can do whatever you need with that to then produce the result. And again, just really high level, giving you a taste for what this looks like in practice. Very similarly, you match on the type that you are expecting from the schema, and then you tell the deserializer, hey, this is what I'm looking for. But then, unlike the serialize, you don't just get the result straight away. You then have to pass in this visitor thing. So there's this extra level of indirection. And the reason that Serde works like this is that this deserialize bool, or deserialize U64, it's actually just a hint to Serde about what kind of type you're expecting from your input. But you might actually get something different. So you pass it a visitor, which Serde, the deserialize will then call one of the methods on it with the actual type that you got. And the clever thing about the trait is that there's a whole bunch of different visit methods, visit bool, visit string, each of which are called based on what you get, but they all have a default implementation which just says syntax error. So it's really easy to just, if you write nothing, then it just assumes it's bad input. So this is the bool visitor as an example. If it gets anything other than a bool, it's going to be an error. If it gets a bool, then it can simply take that value, and builder is what's going to then write it into that encoded byte sequence. So I've had to really gloss over this at a very high level, but just to give one concrete example of why this is more efficient than the simple approach. In the simple approach, it has to deserialize that JSON blindly and turn it into this whole in-memory representation, and then only then can you start validating that it conforms to the schema and turn it into that compressed representation. But in this approach, we're implementing deserialize seed. It actually drives the deserialization. So it allows for these really efficient code paths. For example, if my schema is telling the deserializer, hey, this value is going to be a Boolean, then it filters down through all the Serde code, which is all very fascinating. You should all read it. And it gets to this code where it literally just looks at the next character. If it's a T, it's expecting true, so it just checks that the next characters are RUE, and it's done with the job. If not, syntax error. Likewise with false, and then any other character it encounters, it can immediately throw a syntax error. It doesn't have to waste time decoding all of that JSON text. It just knows straight away, hey, this isn't what I was expecting to see. Now, no performance talk is complete without proving that the thing that you said was more performant actually is more performant. So I did do some simple benchmarkings on my laptop, and sure enough, the direct approach of going straight from JSON to bytes and back again, about 2 or 3 times faster than the simplistic approach. Thank you.
Cool, awesome. One question, by the way. Did you encounter any problems with the fact that JSON is like not sorted? Like you can get any key in any order and these kind of things?
Absolutely, and I had a whole slide about it that I had to cut for time. So with the simple approach, because you're parsing the whole JSON thing into memory, it doesn't matter what order the keys are, it all comes into memory. And then when you're actually iterating it over to turn into bytes, you can just traverse it in the order that you want. So when I went to the more efficient approach, I immediately ran into the problem of, oh crap, the keys are in the wrong order. How do I do that? So there's a lot of different approaches. The one that I went with was to just write it into bytes in the order that I got it. And then once I had the whole object in this flat array, I rearranged it.
Right, okay, cool.
If that makes sense.
Yeah. Questions?
Is this available as a crate? Because it sounds really useful.
So the actual database itself that I'm working on is just kind of my own code at the moment that I haven't made public. But to prepare for this talk, I did make this kind of self-contained example of this process. I just have not had the time to put it on GitHub, but I'll probably do that tomorrow. And I'm happy to share the link in the GitHub, so you can, because it's really interesting, and you can see how it all actually implements properly.
This is not my area of really my area of expertise, but I have used this library called Postcard, and which is the thing where the data itself is not self-describing, and it'll only deserialize correctly if it fits the schema. Otherwise, and with that, I was just noticing you were implementing serialize and deserialize those traits. With Postcard, they don't do that. Like you just do derive, serialize, deserialize on your struct, which is your schema, and like they have their implementation of serializer and deserializer. But I'm just wondering, like, what are they doing? How can they to do that? Whereas you had to, I didn't fully understand that just as a user of these things.
So I'm not entirely sure. What it sounds like is Postcards is binary encoding that, like you said, isn't self-describing. So you do need that original schema in Rust code in order to be able to properly deserialize your serialized output. The difference is that I assume that's going to be your fixed schema. You have certain structs and enums, and then when you put derive on it, all this macro wizardry that's built into Serde is going to generate the code it takes to pull the fields out and put them into Serde's data model, and then pass it on to Postcard, and Postcard will then do all that work. So the reason that I did all this work is because the schema is only known at runtime, and it manifests as this recursive enum that needs to be fed into the serialization and deserialization process, if that makes sense.
I think that's quite awesome work.
Oh, thank you.
So how did you actually end up kind of, solving your own problem? Do you have any kind of, repository in the internet that people can kind of, I'm curious, I want to just try this myself?
Yeah, so like I said, for this particular talk, because obviously my database project is a much larger project, I created a self-contained library crate to demonstrate all the kind of concepts I talked about. And I will put that on GitHub, and I will post a link in Discord. I just haven't had time because I've only had since Saturday to write this talk.
One more question?
Yeah, I was going to ask, I'm not sure if I missed it in your talk, but did you mention the intention behind the database? Like what problem you tried to solve with the database itself?
I guess that's quite an open-ended question, but essentially what's great about CouchDB, amongst other things, is that it is a document database. It has a changes feed, which makes it really easy to do kind of real-time stuff. It has master-to-master replication. It just has all these nice features. The main drawback of CouchDB is it's a bit unloved by the community. It's owned by Apache. I don't want to obviously put down the maintainers. Like, they've done awesome work. It's a great product, but I just wanted to see if I could do something better. And the main motivation for me of doing my own thing is that, like any other JSON database, like HashiB, like Mongo, it's schemaless. I like schemas. I like type safety, but I hate SQL. So I was like, why can't I have a document database that also has a schema? As far as I know, and please correct me if I'm wrong, that doesn't exist.
I'll need to ask you about that later, but sure.
Please do.
That's good.
Cool. Awesome. Thank you very much, Alex.
Thank you.
Let's take a 5 minutes break.
Yeah, quick break because we need to set up the next remote speaker. And we'll be back in like 5-ish.